Hello, and welcome to this week's edition of the Taurus Report, the bull in the china shop of cosmology. So, this week I want to return once again to the idea of how, in cyclic gravity and cosmology, various items in the universe would be recycled. In this recycling process, black holes would play a major role, but probably the largest role is going to be played by quasars, which are giant black holes at the center of galaxies. And so, in this week, we're going to revisit the idea of recycling, but especially in the context of quasars. Now, the reason why we want to look at it in the context of quasars is that active galactic nuclei, which have black holes at the center, those would be the largest, by far, black holes in the universe, and those would be the ones that would do the vast majority of work in recycling. And also, since when we look back at the very early universe through the Webb telescope, the more visible than something like a simple star or a black hole with an accretion disk would be galaxies. And so, if we're trying to get a picture of the early universe and try to base a cosmology upon that, then we would want to look as far back as possible and look at structures like galaxies. We want to look at things on a galactic level. And so this is going to mean looking at quasars back in that time. And so let us proceed with that. The first thing that I would like to take a look at is this paper that just came out just recently, a few days ago, in February of 2023, by Cameron and his colleagues over at the University of Oxford. Now, this paper is interesting, and it may seem odd that I'm right away starting with a paper that does not involve quasars, but he does make a comment here in the abstract that I find fascinating. So, what is it about this paper that I find so interesting? So, in the abstract, we read here about how, and I will put all these links in the comments as usual, so you will be able to access this paper as well by looking at the comments and following the link. So, what they did is they're looking back at this galaxy GN slash Z11. And they're looking at the part that interests me is the production of nitrogen. So, what is so strange about nitrogen? And I just want to remind the viewers of some things that we've talked about before, just to recap a little bit so that it's clear what is so important about this. So, in Big Bang cosmology, if you go back far enough, then you get back to a time like right at the Big Bang where all you have is subatomic particles and photons, and matter is like right at the Big Bang. It's like broken down into its constituent parts. And so in Big Bang cosmology, as time progresses and the universe expands and cools, then you get the formation of heavier elements. Now, for astronomers and astrophysicists in this context, basically anything beyond helium they refer to as a metal, just implying that you're talking about heavier elements further down in the periodic table. And so, according to Big Bang cosmology, there's going to be a time when really all that's there is like hydrogen and helium, and these would first collapse into what are called population 3 stars. So a population 3 star, if we did a spectrograph of it, the only absorption lines we see is hydrogen and maybe some helium. In other words, we would not see spectral lines of heavier things on the periodic table. And again, astrophysicists in this context call anything heavier than helium a metal. Okay, so it may be for someone who's taking chemistry, you don't normally think of like nitrogen or oxygen or things like that as metals. But in this context, that's what they're called. So this paper by Cameron and his colleagues is noting that in this galaxy, there's a very strong nitrogen line. And immediately when Webb started operating, it found all kinds of things that were problematic for standard cosmology. And one of these problems, there's a long list which this video series has explored in detail, and so I'm not going to repeat everything. But one of the problems with what Webb found is the presence of metals very, very early, meaning that stars had to be formed and then go nova. And it's in the process of going nova that you get the energies required to make metals. And so if you're seeing metals, that means that you have at least one or more or several cycles of gas forming a star. The star goes nova. It produces metals that are further down the periodic table. Then the gas congeals again. It forms a new star. Then it explodes and makes even heavier stuff, like, iron or whatever. So Big Bang cosmology explains that all of the elements in the periodic table had to be created in some way like this. And if you get right to the beginning of the Big Bang, none of these elements would exist. Okay, if you look back far enough, none of the elements should exist, and all you should see is hydrogen if we can look back far enough. So what this paper is noting is that in this galaxy, there is, and let's go back to the paper here, there is a very strong presence of nitrogen at a time when this is very difficult to explain. And the authors do note that other theorists presently, standard GRLCDM theorists, have tried to explain how this is possible. They're sort of saying that, and it's kind of interesting the way they phrase everything. I find it kind of disingenuous myself, but they, rather than saying that there's a challenge to their standard cosmology, they're starting to constantly say now there's challenges to the way in which galaxies are formed. And what they mean by that is they're assuming that they can save Big Bang cosmology by sort of fast-forwarding galaxy formation. So if they come up with mechanisms where everything can be fast-forwarded, using things like dark matter, dark energy, or other processes that have not been observed, but which are needed to save Big Bang cosmology, well, they'll just come up with these processes and they'll declare that that's what happened without any evidence, in my opinion. Or they'll put dark matter or dark energy wherever they need it, or in whatever context they need it, in whatever concentrations they need it, in order to try to explain how this stuff is happening in a fast-forwarded sort of way. And so the authors of this paper sort of obliquely, kind of refer to that when they're saying that we find no compelling evidence, and I'm going to highlight this part of the abstract here. We find no compelling evidence that nitrogen enhancement can be explained by enrichment from metal-free population 3 stars. So they're kind of saying that the standard way in which Standard theory explains the evolution of elemental abundances as starting with the Big Bang. Then you have population 3 stars. Then after that, you have a new generation of stars with a higher metal content, and so forth. Uh, the authors of this paper are saying it's probably not that. It doesn't make sense to them that that is the explanation for these metals. And so the authors say something which I kind of agree with and kind of disagree with, and I'll explain what I mean by that. So they say instead, we have some promising proposals of stellar collisions, like let's say back in that time where you have population 3 stars, like they run into each other. Okay, dense stellar clusters and tidal disruption events just means stars very close to each other, pushing and pulling on each other and ramming into each other, providing the energies needed to create these metals. Now, I disagree with that. I think that that's probably not true in any way. Okay, I doubt that that's a way to explain this. However, the one promising solution that I kind of agree with is when they say they note that the unusual emission lines are sort of similar to a nitrogen loud quasar. And just that one little sentence in their abstract, just that one little sentence, I kind of agree with that quasars, if you look at quasars or the mechanisms within quasars, you're likely to find some way of explaining metals. Now, I would disagree with it in the sense of if you're going to try to say that the universe had no metals at all, and suddenly quasars suddenly kind of magically appeared, because a quasar itself is a giant black hole, right? A quasar itself is a giant black hole with matter accreting into it. And so I'd like to discuss that a little bit. I'm going to go from here to discuss a little bit about quasars, what they are, and then I will return to why I kind of agree with this sort of observation in the paper in some sense. I mean, I disagree with it in the sense that it saves the Big Bang, because I don't believe it saves the Big Bang. But I do agree with it in the sense that I do think quasars can be a source for metals and for everything else for that matter. So we're going to kind of delve into quasars and how they're related to this in a minute here. Here at this NASA site, which I will include in the comments, is an artist's conception of a quasar with a jet. So a jet is this sort of whitish outflow of material from the quasar. And then when I say accretion disk, I'm talking about this cloud of gas going around the black hole. And this black hole is not an ordinary black hole, but a huge, gigantic one at the center of a galaxy. And so this is the type of quasar I'm talking about. Now, not all quasars have jets like this where they're expelling material going out like that. And this article notes that they have just recently discovered that the only quasars that are shooting jets like this out are those with accretion disks around them. You know, this giant disk of dust and gas that is slowly cycling into the black hole at the center of a quasar. So the reason why this is important is that under CGC, cyclic gravity and cosmology, I have noted that one of the consequences of the theory is that all masses in the universe can only occur at certain discrete size and density concentrations. And so everything must be a certain discrete size and density. And if it is not at one of these specific size density combinations, then it is unstable. Whatever it is unstable. And so the excess material will be expelled out. As I noted in a prior episode where I talked about the asteroid Bennu and the Osiris mission to Bennu, this was, in my opinion, an example of something as small as an asteroid that was at an unstable size where at the surface of Bennu, gravity was tremendously weak or even repulsive in some places. And the surface of Bennu was not compact. It was much more like the comparison was to balls at a bounce house playground for kids. So when they tried to land the Osiris spacecraft on it, it was kind of sinking in, and they rescued it by jetting up right away. And they also observed on Bennu all these little pebbles, shooting off into space. And I reference that in my paper, and I want to, again, before I go on about quasars, my point in bringing up Bennu is that even in certain items within our solar system, like the behavior of Oumuamua, which I also speak about in my paper, or Bennu, or even the braided rings of Saturn, or the flyby anomaly, or the Pioneer anomaly, or the performance of the Russian satellites in Molniya orbits, various things right here in our own solar system have shown that gravity behaves differently in certain contexts than what is predicted by GR. And so in my paper, I explain why that is, what gravity is, and it is presented as a relic of the electromagnetic force. And so it will, over distance, generally trend down with distance, just as in Newton's gravity or Einstein's gravity. This is also the case. But in addition to trending down, just like Newton and Einstein's formulas, it also has some wave-like characteristics in the graph, and at certain distance, gravity can even become repulsive. And I explain all about it in my paper, and I'm going to digress for a second to remind everybody how to access my paper, and to just show briefly how my paper explains all this. But the point to keep in mind is that, again, only certain discrete sizes and densities are stable. If you get beyond that, then it becomes unstable, and that mass will split apart. And that is, by the way, why most star systems in our universe are binary. Most are not a single star like our sun. Most systems that you look up at in the sky at night, most of those are binary systems. And it means that it is normal for the masses to get to a certain discrete size, and then there's excess mass, and that is expelled outward, and it forms another star. And that's why most systems are binary with two stars orbiting around each other. But anyways, to remind everybody, if you open up a browser tab and you type Torus Report, all as one word, .com, it will bring you to my website. And then at my website, you can see the episodes. You can explore the links up there. All of the videos are on Spotify if you just want to listen sometimes. There is a YouTube playlist where you can see every episode in order. And there's also the videos in order on Facebook, if you prefer that. But the thing I'd like you to note is my paper on cyclic gravity and cosmology. If you click on that, then it comes up, and I like to download a PDF. And so the PDF I like to zoom to fit with. And so if you look at that paper, in the beginning of it, it explains how and why gravity has this form that I'm claiming. And there's several sections that explain exactly how and why it has this form, along with mathematical expressions for this new form. And as you come down, then you will come to the parts about black holes, which is relevant to what we're talking about today. And so what section is that? Excuse me a second while I just scroll down to this section. The paper is 23 pages total. And so, one brief thing I want to talk about here in reference to black holes. First of all, in CGC, the term black hole is a little misleading because in CGC it does not mean what it means in general relativity. In general relativity, black hole means there's an event horizon where light can never escape, and typically there is a singularity or a region of infinite density at the heart of a black hole. Now, CGC does not present black holes in that way, and so when I'm using black hole in the context of CGC, I am referring to a neutron star. So there is not a singularity at the heart of it. There's just a neutron star at the heart of it, and it has sufficient mass and appropriate size to attract a very large neutrino density that refracts light. All gravitational sources do this, according to CGC. But in the case of a black hole, this neutrino density is so large and the concentration gradient is so strong that light is totally internally refracted, meaning that light does not escape because it is internally refracted. It is not due to gravity. Now, this also means that in CGC there is no such thing as an event horizon, in the sense that once you cross that in general relativity, it is impossible to escape. Even light can't escape. Under CGC, that is not true, because if you keep dumping mass into a black hole, so like if the black hole has an accretion disk and mass and gas and dust is constantly falling into it, then eventually the black hole, or the neutron star, according to CGC, will reach an unstable size, and it will start breaking apart or ejecting the matter. So the next section after this is where I talk specifically about black holes. So it's in section 16. That's where I talk in depth about black holes in the paper and explain everything that I just said. And so the point that I want to make here, and now why is it relevant? Why is everything I said relevant to quasars? So I wanted to bring that up to make the point that under CGC, mass can escape a black hole. And I want to delve into that next, especially in the context of quasars. So now coming back to this diagram here, using the information that I just spoke about. So at the heart, you've got this black hole here, and if you read all the literature about quasars, they're always saying how they cannot understand the mechanics of how these jets are formed exactly. And they always speak of it in these terms because, according to general relativity, mass cannot enter the black hole, right? In the sense, I'm talking about this mass in this white jet here. That mass could not have come from the accretion disk in the sense of entering into the black hole and then being ejected. According to standard theory, that cannot be happening because anything that goes past the event horizon of the black hole can never escape. I mean, once you go in, there's no coming out. So, what does that mean about these jets under standard theory? What does that mean? So, under standard theory, their idea is that the accretion disk is spinning around, and then as it kind of falls in, it starts spinning around real fast and makes like a little vortex around the black hole and then gets ejected vertically. So, in other words, they're saying that maybe the jet is caused by the accretion disk. So, they might agree with me on that, so that this stuff coming from the accretion disk, it goes in, but they would say it does not pass the event horizon, right? It spins around real fast down here and then gets ejected up here. Whereas under CGC, it is perfectly allowable for mass to fall into a black hole. There is no such thing as an event horizon. There's no such thing as an event horizon. And under CGC, then if that black hole is near one of its size limits that I spoke about earlier, if it is near one of those discrete sizes, then it is going to want to eject whatever matter falls in. So stuff might be attracted, and it gets on because of its velocity due to its attraction out here, right? Because of its velocity, it plummets into the black hole. Then when it gets near the surface, because the black hole is at one of those discrete sizes I was talking about, then gravity right at that surface, as it gets a little bit larger, suddenly becomes repulsive. Now, because within a black hole or a neutron star, you have such an extreme environment. I mean, I don't know, like some of these neutron stars, don't they spin something like, 1,000 revolutions a second or some ridiculous amount for something that size? To think of it spinning that fast is ridiculous. But my point is, very extreme environment. Okay, so if gravity is repulsive in that environment, it would be extremely repulsive. So that means that matter can be falling in because of the accretion disk, and then it can be violently ejected in these jets that we're seeing. And under standard theory, it's kind of tough to explain all this because they've got to explain the repulsion in terms of electromagnetism, but the accretion disk in terms of gravity. And so under standard theory, somehow you have all of this stuff here attracted in because of gravity and then repulsed out because of electromagnetism. But it can't actually fall into the black hole. It has to spin around really close, suddenly become magnetized or charged or something, and be ejected out here, in this jet. And so we can see that is quite challenging for standard theory to explain all that. Now, under CGC, because gravity itself, because gravity itself is a relic of the electromagnetic force, in an extreme environment around a black hole like that, you could have attraction and repulsion, both very violent and doing very odd things like this. Now, after all of that said about what a quasar is, a quasar with a jet, what that is, let us go back next to relate this to what we first talked about, which is metallicity in these early galaxies. I explained earlier that the formation of metals is thought to happen through successive generations of stars going supernova, because it takes or nova, it takes the kinds of energies that we have within a nova to allow fusion into higher elements, the metals. Now, I note that going back to the paper that I discussed in the opening segment of the show today, going back to that paper, this paper by Cameron and his colleagues over at Oxford, where he notes that some of the observations give line to similar emission lines where there's a resemblance between this galaxy GNZ11 and a nitrogen-loud quasar. And so I am going to claim that the implication there is that quasars provide us with a violent environment where vast energies are present that can also explain the creation of metals. So now the difference here between what CGC is saying about this whole subject and what Big Bang cosmologists are saying is that for CGC, this type of process is an ongoing, constant thing in the universe. So you would have galaxies go through various life cycles where they're creating metals, and exactly what's going on in the jet, I mean, I'm not sure. You could have creation of metals, but you also might have creation of free hydrogen gas from metals that fell in through the accretion disk, and those metals could be recycled. Like, let's say you have super heavy metals like, I don't know, uranium or whatever, falling in. Well, because CGC allows for that stuff to fall all the way to the surface of the neutron star, that means that matter can be totally recycled. You could take a very heavy element like uranium, and it could be ejected from that black hole. According to CGC, this uranium could be ejected as hydrogen. And so under CGC, we would have this constant cycling of material, and the largest recycler would be the black holes at the center of galaxies. And so this means that while CGC would agree with the Cameron paper in the sense that there might be a similarity that has real meaning here, in that these quasar jets might be producing metals. Okay, of course, under CGC, they might also produce hydrogen. It would take a lot of detailed observation and further research to say exactly what's happening. But under CGC, this would be a constant recycling process that is going on all over in the universe. And so CGC really does not need to explain the abundances of elements, like starting from hydrogen and then getting the current abundances that we see, because under CGC, the relative elemental abundances of all the different elements in the universe stays approximately constant forever. Now, CGC does posit that the universe may have gentle expansion and contraction, but this expansion and contraction is not cataclysmic. In other words, it doesn't contract all the way to something like a Big Bang. And it doesn't expand all the way so that you have a dead universe according to entropy, where eventually everything gets so dissipated you have it essentially a dead universe. So neither of those cataclysms happen under CGC. Instead, you have a universe that's sort of pulsating, just gently expanding and contracting forever. So, under this cyclic cosmology, then elemental abundances would stay approximately equal, maybe with some variation over time, but not cataclysmic variation. And there are various things under CGC that approaches like almost every question in cosmology. CGC just approaches it in a different perspective. So I'd like to just take a look at next at some recent, another discovery involving black holes, and then also a recent paper positing sort of a bounce cosmology, which has a superficial resemblance to CGC. But let's take a look at those things next. Now, the paper about the black holes I was just referring to is this one, where we've got a black hole 1 billion times the mass of the sun, and it says could upend our understanding of galaxy formation. So this is something seen with Webb, another black hole, essentially a quasar, I think. And they're saying it upends galaxy formation. And this sort of bothers me, the way they keep doing this. Look, it doesn't just upend galaxy formation. It upends your whole Big Bang cosmology. You have this theory that says everything started as this, super plasma at the Big Bang, where everything is broken apart into, subatomic particles and so on. And as it expanded, you start getting ordinary matter. And then quite some time later, you'd have areas that might congeal enough to form like a massive black hole. But there just isn't time in your cosmology for us to have such a huge black hole that early. There's no time for the gas and dust to congeal to form this thing. And so when you say it challenges galaxy formation, I mean, come on. Yeah, it's not just challenging galaxy formation, because you keep trying to say that, oh, we can explain it, everything happened in fast motion. It's like, well, I mean, fine, you can say that, but you're not really explaining it. You're just saying, oh, in this portion, this early, like right after the Big Bang, we're just going to fast forward everything. And we're not going to explain how that's possible, but, if it worked really fast, then we'd be able to explain it. And it's like, well, I mean, no kidding. Yes, if it happened really fast, you could explain it. Anyways, so that is one thing that I wanted to discuss. And then there was one more item I wanted to bring up here. So this paper came out recently, which talks about dark energy. And immediately, I don't like that. I don't believe that dark energy exists. And it presents sort of what's called a bounce cosmology. And I talk about this in my paper as well. I do reference an example of bounce cosmology in my paper. And so what is all this about? What is bounce cosmology? So bounce cosmology, it has a superficial resemblance to CGC in the sense that CGC does allow that the universe is gently expanding and contracting forever, sort of like this pulsating expansion and contraction. And so it's stable over time. Steady state is kind of a misnomer in the sense that, yeah, because that repeating cycle goes on and on forever, it might be thought of as a steady state. But it's not really a steady state in the sense that at some times the universe is going to be less dense and sometimes it's going to be more dense. But in CGC, space itself does not expand and contract. This is due to the simple cyclic operation of electromagnetism. which again is explained in the paper. Now, these bounce cosmologies that are being proposed, the superficial resemblance is that you also have this expansion and contraction. The idea of the universe getting large, getting small, getting large, getting small. But there's a big difference in that in these bounce cosmologies, they are talking about space itself expanding and contracting. Okay? Now, under CGC, space is never deformed. It does not ever expand or contract. It stays constant. And so, also under these bounce cosmologies, you might have cataclysmic events like everything consolidating into a Big Bang again and then repeating. Now, like all theorists that rely on general relativity, they don't really give any explanations for this. They just have mathematics and say that, oh, it does this. And then they'll use some fancy term, like for dark energy, they'll say something like negative vacuum pressure or whatever, to give it this aura as if they're saying something scientific. But in reality, it's just a stopgap saying that we mathematically describe an expanding universe here, and we have no clue why it does that. But we'll call it something like negative vacuum pressure because then we can use, fluid dynamics and so forth and describe it with that kind of mathematics. But there isn't any actual fluid there. They're just using that mathematics because it's convenient, but it isn't real. Okay. Anyways, as you might gather, I dislike that kind of thinking. Now, in general, I prefer where we try to adjust our understanding of gravitational law in order to match what we're observing. And standard GR-LCDM theorists, they do not do that. What they do is they insist that GR is correct in spite of everything they see out there. Okay, galaxies are accelerating away from each other, right? Galactic rotation rates and so forth, all the stuff we've been discussing in this video series. And so they refuse to adjust their gravitational law. So what they do is they make up reality to match their law. Okay, they can't make their law work. So they make up stuff like dark energy or dark matter. And that's just making up reality to fit your equations. And I strongly disagree with that approach. Now, in arguments with some GR-LCDM theorists, and they look at what I'm proposing, and they say, look, all you're doing is data fitting. You're looking at gravity in a certain context, and then you adjust your law because you have a series of sine waves. And they're right. I can adjust my law to match the data. And so their criticism's absolutely right when they're criticizing me on that. It is data matching. However, I explain why the true law of gravity is so ridiculously complex in my paper. And I make the case that at this stage in time, we cannot do anything except data fitting. In other words, I am claiming that right now the only appropriate thing to do is to have ad hoc, temporary, ugly, cumbersome expressions for gravity to specific contexts. Okay? And so what I'm saying is, for now, we need to let go of the idea that we can come up with a simple and elegant force law that applies to gravity in all contexts and in all places. Forget that idea. We can't do that right now. What we need to do is data fitting in specific contexts, where we observe a very specific context. We say, in this context, at this time, and at this place, bodies are moving in this way. We assume it's due to gravity. We don't have a elegant, easy, simple equation for it, but we can match data points, and we can just say at this, in this context, and at this scale, and at this location, this is how gravity behaves. Now observe that even in a case like that, you can have an object come in from out of that system, as was the case with Oumuamua in our solar system, which I discussed also in my paper. You have an interstellar visitor, and because it is not acclimated to our system, it is obeying a different gravitational force law, and so it did not behave as predicted. And so even if you have gravity modeled in a specific system, if you get some kind of interloper from some other system that comes through rapidly, you might get a different result. Okay? And so I'm claiming that, and I give very good reasons why, if gravity is structured in the way that I'm claiming, that you can't have an elegant, simple law right now. And so I'm sort of appealing to everyone to sort of explore the CGC idea a little bit further. Now, there are a few theorists out there that, in my opinion, are actually trying to approach this in a scientific way. One of them, Eric Lerner, he's been mercilessly pilloried in the scientific literature and in the general press. But I respect the guy. Okay, I don't agree with plasma cosmology on several points. Plasma cosmology is Lerner's theory. But what I respect about what he's trying to do is he is trying to observe the way matter and energy is behaving in our universe, and trying to adapt known force laws, known particles and antiparticles, in a systematic way to explain what we're seeing. And what I respect about Lerner is he's not going off and making up, things like dark matter and dark energy. Now, I disagree with some of his theory in the sense that I don't think that there are vast areas of antimatter out there. But I would like to get into that a little bit next week. I'd like to look at the very few people who have proposed alternative cosmologies and give them credit in areas where I might agree with them, and also critique the views in areas where I might disagree with them. But that is it for this week. Thank you so much for tuning into the Taurus Report, and we will see you again next week. Goodbye for now.